Welcome to this tutorial on electrics for heating engineers. The aim is to just give you a basic grounding on electrics and electronics to make your job easier. So what is electricity? In simple terms, electricity is the flow of electrons along a conductor from an area of electron surplus to an area of electron deficit. Some terminology that we'll be using. Conductor. A conductor is a material that gives up its electrons easily, allowing electricity to flow freely, such as copper, aluminium, gold, silver, and most metals. An insulator is a material that holds onto its electrons tightly, preventing the flow of electricity. Most non-metallic solids are good insulators, particularly things like plastic, glass, etc. Electron. An electron is a negatively charged particle in an atom. Atoms are comprised of a nucleus which contains protons, positively charged, neutrons which have no charge, and electrons which orbit around the nucleus. Voltage. Voltage is the amount of pressure pushing the electrons around a circuit, measured in volts, for which the symbol is V. This is similar to the water pressure in plumbing. Current. Current is the amount of electricity flowing in a circuit. It's measured in amperes, symbol A, and can be compared to the flow in a pipe in plumbing. Circuit. A circuit is a complete path allowing the flow of current. You'll see more about this later. DC and AC. You will have heard these terms and might know or might not know what they are. DC equals direct current. Current in the circuit flows in one direction from the negative to positive. A battery supplies DC. If we were to look at a graph of voltage against time for a DC circuit, it would show a flat line. AC equals alternating current. The current constantly changes direction at a set frequency. In the UK, the main supply is at 50 cycles per second, or 50 Hertz. Graph of voltage against time will show a sine wave for an AC circuit, as in the diagram below. Supplies are quoted as volts DC or volts AC, for example, 12 volts DC or 230 volts AC. So let's go on to some simple circuits. For a circuit, we need a voltage source, which can be a battery, it could be a power supply, but we'll use a battery, and a load. With the switch open, no current flows and the light is off. If we close the switch, then current can flow. Electrons move from the negative terminal of the battery through the lamp to the positive terminal, and the light is on. It's the energy in the electrons that make the light glow, whether it's an incandescent lamp or an LED. Then we come on to a series circuit. In this circuit, the two lamps are in series, i.e. in one loop. All the current flows through both lamps, so the current measured at A1 would equal the current measured at A2. A parallel circuit. In this circuit, the two lamps are in parallel, similar to radiators connected to flow and return. So all the current from the battery flows through A3 and returns through A4, and will be equal to the sum of the current flowing through A1 and A2. If the lamps are identical, then the current at A1 will be the same as the current at A2. Current measurement. To measure current, we connect an ammeter in the circuit. The current at any point in a series circuit will be the same, as we've already said. So in this circuit, the reading at A1 will be the same as the reading at A2. Voltage measurement. To measure voltage, we connect a voltmeter across the circuit. The voltage can be different at different points of the circuit. So in this circuit here, V1 will measure the voltage across the battery, which is 9 volts in this case. V2 and V3 will measure the voltage across each lamp. And again, if both lamps are identical, then V2 and V3 will be the same and will be 4.5 volts. Ohm's law. Ohm's law states that the current flowing through a resistance is proportional to the voltage drop across the resistance. This is one of the fundamental calculations we use in electrical work. If you've already done the Maths for Heating Engineers tutorial, you'll remember the triangle, the Ohm's law triangle. We can say that V equals IR, volts, amps and ohms. These are what we're dealing with. So if we take our simple battery and lamp circuit, if we want to know the current flowing through the circuit, we cover up I on the triangle, and that tells us that I equals V over R. Therefore, the current in this circuit, if our lamp has a resistance of 18 ohms, will be 9 divided by 18, which is 0.5 amps. It could also be shown as 500 milliamps. In this example, we actually measure the current as 1 amp. Ohm's law tells us that R equals V over I. Therefore, the resistance of this lamp would be 9 ohms, 9 over 1. To add up resistors in series is very simple. We just add them together. So our equation is R total equals R1 plus R2 plus R3. So in this example, if each of the resistors are 10 ohm resistors, the total will be 30 ohms. Resistors in parallel is a different story. And the equation to work out the total of resistors in parallel is 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3, etc., depending how many resistors you have. So in this example, if each resistor is 10 ohms, 1 over R total, RT, equals 1 over 10 plus 1 over 10 plus 1 over 10. So 1 over RT equals 3 over 10. Therefore, RT equals 10 over 3, which is 3.33 ohms, 3 1/3 ohms. Some quick tips. For resistors of equal value in parallel, for 2 resistors, the total will be the value of each resistor divided by 2. For 3 resistors of equal value, the total will be the value of each resistor divided by 3, etc. For example, if you have 200 ohm resistors in parallel, the total resistance will be 50 ohms. If you have 300 ohm resistors in parallel, the total will be 33 1/3 ohms. If you have unequal resistors in parallel, the total will always be lower than the value of the smallest individual resistor. Now we come to resistors in combination. So in this circuit, we've got 2 resistors in parallel and then 1 in series. So we have to work out the parallel resistors first. So if R1 is 10 ohms, R2 is 30 ohms, and R3 is 30 ohms. For R2 and R3, 1 over RT was 1 over R2 plus 1 over R3, which equals 1 over 30 plus 1 over 30. Therefore, RT equals 30 over 2, which equals 15 ohms. Now we simply add R1 to the calculated value for R2 and R3, so the total resistance of the circuit is 10 plus 15 equals 25 ohms. Now we come to calculate the current flowing through each resistor. As we've already said, R1 is 10 ohms, R2 is 30 ohms, R3 is 30 ohms. The total current in the circuit equals V over R total, which we calculated from the previous slide to be 25 ohms. So the total current in this circuit will be 9 over 25, which is 0.36 amps. The voltage drop across R1 equals I times R1, which is 0.36 times 10, so the voltage drop across R1 is 3.67. The voltage drop across R2 and R3 will be 9 minus 3.6, which equals 5.47. So the current flowing through R2 equals V2 over R2. which is 5.4 divided by 30, equals 0.18 amps. The current flowing through R3 will be V3 over R3, which is 5.4 divided by 30, which equals 0.18 amps. Now we come on to electrical power. Again, we can use our triangle, and power in watts equals the voltage times the current in amps. So we've already calculated that the total current in the circuit is 0.36 amps. So the total power consumed by the circuit is V times I, which is 9 times 0.36, which works out to 3.24 watts. We also know that P equals VI. We also know that V equals IR. So we can also express power as I times R, or I squared R. We know from previous calculations that the current at R1 is 0.36 amps. Therefore, the power consumed by R1 is 0.36 times 0.36 times 10, which equals 1.296 watts. We also know from previous calculations that the current at R2 and R3 equals 0.18 amps. Therefore, the power consumed by R2 is 0.18 times 0.18 times 30, which is 0.972 watts. The power for R3 will be the same as R2. If we add the power for each resistor together, 0.972 plus 0.972 plus 1.296, we get the total power for the circuit of 3.24 watts, which is the same as our previous calculation, so we know it's correct. So to summarise, in this module we've learnt about series circuits, parallel circuits, how to measure current, how to measure voltage, Ohm's law, and how to calculate power at various points of a circuit. The next module will go on to putting all this into practice and simple testing of circuits for fault finding purposes.